Okay, let's get started. So today we're going to talk about motion now in 2 dimensions, and we'll look specifically at projectile type problems. Here we're going to use the example of a projectile under gravity, but in a chemistry situation, we may have an ion near a charged surface, and we would have very similar dynamics. The functional form, the mathematical functions would be the same, just the constants would be different. We'd have electrostatic forces instead of gravitational forces. Well, we'll look at 2 cases. One, a horizontal launch off of say a building or something, and then a launch from the surface, a surface launch. And of course, in general, you could launch from any position in any direction. Okay, well, let's start here. If we're doing a horizontal launch, then we're coming to the edge of this at a certain velocity, Vx, and there is no upward or downward velocity. So that's why we say this is a horizontal launch. Now, let's think about the conditions that this projectile is under for both the x and its y components. Okay? So for the x direction, it's experiencing a constant velocity. We're ignoring any kind of friction due to or drag due to the wind or due to the air. And so there's no forces acting on it in that direction. If we were to draw a free body diagram, it only has a weight force pushing it down. So there's no net force side to side. So side to side motion is uniform motion. Y is then a free fall problem, right? So that's what's so great about being able to decouple the 2 orthogonal directions, x and y, because we really just have 2 one-dimensional problems which we've already worked on. So we have a constant velocity problem and we have a free fall problem. So let's just record what we've already learned from the free fall. And we have a free fall time. Right? So we developed that last time. And so that gives us the time it takes for this to just drop. So if we imagine just looking at the y direction, so if we had a light here and we showed a shadow of this object, how long would it take to drop? And that's how long it would be in flight. So square root of 2h over g is the formula we had gotten from before. Now let's use the constant velocity kinematic equation. And a good thing to do would be to call our initial x position 0 here. So then this will drop out. And we will simply have the v, or I guess vx here. But that would be equal to the total velocity because we're moving in the x direction. And so our total distance, this distance, okay, we're moving at that constant rate, boom, we hit the ground, and we hit the ground right here. So v square root of 2h over g. So notice, if we're going faster, we'll go further at the same height. If we're on a higher building, we would go further with the same velocity. And g is constant for Earth, but if we were to go to the moon or to Mars, this would be smaller, and so the same velocity would give us a further distance. So we can understand the parameters there in that equation. All right, well, let's turn our attention to a surface projectile. So here, let's say we fire this cannonball or something, and we have an initial velocity, v, that consists of now a non-zero x and y component. And here it's best to consider the angle of launch, theta, and then the magnitude or the speed, the launch speed here. So here's the speed, and here's the angle. And by trigonometry, the cosine x is this is vx, and this is vy, the 2 vector components of this velocity vector. Again, in the y direction, we face the constant acceleration. So we have the constant acceleration kinematic equation. In the x direction, we have a uniform motion. So we use the uniform motion kinematic equation. All right, the conditions here now, I think it's, let's look at now the y component. We're starting at height 0 and we're ending at height 0. Right? So we go up and down. So essentially it's a leap problem, which we did last time. But let's just use the kinematic equation directly. And so we can put in 0 here and 0 here. So 0 equals 0 plus all this. And we see it looks like we might be facing a quadratic equation if we're going to try to solve for delta t. But there's a delta t in each of these terms that we can pull out. And this whole thing is equal to 0. So this would be true, this equation will be true if delta t is 0, but that's not really a physical solution because we know that delta t is going to be at least something greater than 0. So the key to this equation is just this. So we have to set this equal to 0, which we do down here, and then bring this component to the other side, this term to the other side, and now we could solve for delta t. So it really is just a linear equation. And this is our formula then for the time at which the projectile would be in the air. And we could see that depends on the velocity, which makes some sense. Depends on, are we on Earth or on the moon? So it depends on the gravitational acceleration. And then it depends on the angle of the launch. So if we just skim it across the ground, it'll hit the ground right away. If we shoot it straight up in the air, that will be the maximum time of flight given for a given velocity. Okay, well, now we've figured out how long it's in the air. What we want to do is get the height and the distance, and that will pretty much describe the things we would want to know about this projectile. So for height, we can use some facts from last video and split the full time into a rise time and a fall time. And we know by symmetry, the rise time and the fall time will be the same. And then we can use our formula for fall time from a height, because that would be this height. That would be that height. So if we can figure out this amount of time, the time it takes to complete that or fall from that height, which we can because it's just half of the flight time, then we can get our height. So here's our full flight time, 2v sine theta over g. So half of that is just going to be v sine theta over g. And therefore, and from before, this is from our free fall equation from the last video, free fall. We could solve for h. And we get h equals 1/2 g delta t fall squared. Well, what is delta t fall? That's this. So we can plug this into here. And we get this as our expression for height. So a little more complicated expression of the angle and the velocity. It's a square of that. Okay. Well, distance. This would also be called range. What's the range of that projectile? So we'll assume here this is we're at x equals 0. How far is this? So we'll use this kinematic equation, the kinematic equation for a constant velocity. But x initial is 0, so we simply have this. This is our full time of flight. This is not just the fall time from above. This is the full time of flight, and that's how much time it has to traverse this distance. And so that's this here. So this component here, this is Vx, and this is our delta t time of flight. Cleaning that up a little bit, we get the range as 2v squared over g cosine and sine. Well, you can plot this as a function of theta. And it turns out that 45 degrees is the optimal angle to get the most range at a given velocity, which I guess makes some intuitive sense. All right. So again, there'll be a lot of problems in your textbook about this, regardless of what textbook you've chosen to work through. So I would definitely work some of those problems. They'll try to give it to you in a little more challenging ways at times. Maybe you're shooting a cannon from up here. Some of the harder problems are when you're trying to hit a certain height that isn't at the apex. So be on the lookout for some of those problems. Those will be good to challenge yourself with. But yep, just try to get competent in these types of projectile motion problems.